Hello, good morning. This is Nas from NB Network Lessons. Hope everyone's doing okay and having a fantastic day. Date today is December 17th, 2025, and I am going to start teaching you calculus. I'm going to start teaching you calculus from scratch. So if you have any fears of calculus in your mind, go ahead and put them aside, push them aside, because I'm going to break it down for you and make it so easy that you should be acing in your exams. So before I jump into teaching calculus and get into solving problems and showing you, graphs and everything, I would like to discuss what are the uses of calculus in real life. I don't think professors talk enough about uses of calculus in real life. What can you do with calculus? Well, with calculus is you can design bridges. When you design bridges, you have to use calculus. Okay. Uh, Optimize business profits, you use calculus. Fuel efficiency, you use calculus. Just about any app you use on your phones has a calculus algorithm in there. Okay, so that should be a motivation for you, that if you're trying to become electrical engineer, if you're trying to become a programmer, if you're trying to become a scientist, calculus is going to come hand in hand. So without any further ado, let's go ahead and dive in. So basically, my aim over here is not to cover 100% in your book, but I'm going to give you the conceptual background, and I'm going to solve enough problems that you will get a hang of it. Okay. So let's go ahead and take a look at this graph right here. So you have this graph. On the x-axis, we have time. Okay. And then on y-axis, I have position. Okay. So basically, if you've got an object, right, let's say this object right here is moving at a constant speed, it's not accelerating, it's just moving at a constant speed. How would you plot it? Okay, well, let's see if this is 1, 2, 3, 1, 2, 3. All right. So in 1 second, let's say these are position is in meters, it's actually distance. So at 1 second, you cover 1 meter. So you write here. Okay. At 2 seconds, you cover 2 meters. So you write here. At 3 seconds, you cover 3 meters. So you write here. So your graph is going to look like a straight line, just like that. Okay. So this is basically a graph plot of position versus time. All right. Now let's look at another graph. So let's plot a graph for velocity versus time. What is velocity? Velocity is basically speed. Okay. So now basically, let's say you're in your car and you're consistently driving at 20 miles per hour. Okay. Or so then you're going at a constant velocity. You're not, your speed is not increasing. So you're going at constant velocity. So how do you plot that? Well, so basically, the graph for that would be a straight line, just like that. All right. This is graph of velocity versus time, because your velocity is not changing. Let's say you are going at, I don't know, maybe 20 meters per second. All right. You're not changing. So this is your graph. So that's velocity versus time. This is position versus time. Now, let's jump on to acceleration. All right. So let's say we have time versus acceleration. How would you plot that? Now, let me ask you this. What is acceleration? Acceleration is when you're going in your car, you put your feet on your gas, and when you put your foot on the gas, you give more gas, all right, your speed increases. Your speed increases, I don't know, maybe with an acceleration of 5 miles per second. So every second, your speed is increasing 5 miles per second. So you have that, that's, acceleration. Now, in this case, we said position versus time. We have a straight line. Then we said velocity is 20 meters per second, but it's not increasing. All right. So then what about acceleration? How would you plot acceleration? Is acceleration changing? No, acceleration is not changing. Acceleration is same. So then the graph of that would kind of look like this right here. It'll be right along x-axis because there is no change. It's constant acceleration. So that is the graph of acceleration versus time. All right. So now let me ask you this. Do you think I've shown you derivative? Okay, because that's what we are after in this topic, is to learn more about derivative. Derivative is nothing but a slope. Okay, slope of a line. All right. And what is a slope of a line? Slope of a line is rise over run. So in this case, if I say, let's say if I take slope at this point, so then this is my rise, okay, and this is my run. So then slope over here would be equal to 3 over 3, which is 1. So you calculate slope anywhere along this line, it's going to be same. Okay, that is the reason we have constant velocity. Derivative of position is velocity. Derivative of velocity is acceleration. So we did derivative 2 times. So how's that? So now I just kind of wanted to show you guys. So if I want to write this, all right, position as a function of t, okay, position as a function of time is equal to m, which is slope, into times. This is standard. Everybody knows that in order to find a slope on a line versus time, function of time is slope into time. Okay. So now this slope, this m, can be any number, can be any number. Okay. Moving on. So if I, what do you think if I take, how can I show you this velocity as a function of time? Okay. So in this case, if you look right here, velocity as a function of time, what do you think it is? It's a constant. It's not increasing, it's staying same. So derivative is slope, rate of change. Rate of change is the key word. Put that in your head. Derivative is rate of change. Is there anything changing in this? No, it's straight line. So I'm going to put constant. All right. Now let's look at acceleration. So let's say acceleration as function of time. What do you think it is? You guessed it. It's 0. It's not increasing. All right. Acceleration is not increasing. You're in your car. You're going at a constant speed. Okay. Acceleration is when you go up, up, up. Speed is increasing every second. That's your acceleration. So now when we come to, let's say you have a, for example, you have something like this, and you have a, I don't know, maybe a curve like this. Let's see, curve like this, right? This is your time, and this is your position. So in this case, you can see the position is changing every second. It's going up. So guess what? The slope we take at this point is basically a tangent. If you look at right here, it's a tangent right here. Then you take slope right here. It's a tangent right here. So at every point, your slope is changing. All right. So then in that case, your position is changing rapidly versus time, if that makes sense. So then we can write this as P position as a function of time is equal to t square. This is basically I'm representing the graph t square, because if you plot a graph for t square, right, you will notice that if you put 1, it's going to be 1. If you put 2, it's going to be 4. So your position is changing rapidly versus time. So this is p is equal to position function of time is equal to t square. Now velocity, so this, let me put this down right here. Pt is equal to t square. Okay. Now velocity going up, you are accelerating, right? Okay. So then velocity of time, if I'm taking derivative of this is going to be 2t. Why is going to be 2t? Because it's constant. It's not changing. 2 times t. All right. 20 meters per second, or I can just put this as, I don't know, maybe 2 over here, right? So your basically your speed is constant versus time. Now let's move on to acceleration. So if you have constant acceleration, okay, so a as a function of time is going to be equal to what? It's going to be equal to just 2. So that means you are basically accelerating 2 meters per second. So your speed is going up, 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 up every second, and you're going up 2 meters every second faster. So hope this makes sense to you. Watch this video a couple of times. I'm going to come back and do lesson 2. Stick with me. I'm going to make you master of calculus. Thank you so much for watching.